Next question, 2.17. A rod is subjected to a uniaxial load within linear elastic limit. When change in stress is given, change in stress is equal to 200 megapascal, change in stress is equal to 200 megapascal, and change in strain is equal to 0.001. Change in strain is equal to 0.001. If the Poisson's ratio of the rod, Poisson's ratio is also given, mu is equal to 0.3. The modulus of rigidity, we need to find out modulus of rigidity, and the relationship between modulus of rigidity and Young's modulus is equal to E is equal to 2G into 1 plus mu. Young's modulus is the stress by strain. Here change in stress and change in strains are given. So Young's modulus we can write Young's modulus is equal to change in stress by change in strain. This is equal to change in stress is equal to 200 and change in strain is 0.001. This is equal to 200 into 10 raised to 3 megapascal. 200 into 10 raised to 3 megapascal. And we need to find out G. G is equal to Young's modulus divided by 2 into 1 plus mu. G is equal to Young's modulus is equal to 200 into 10 raised to 3 divided by 2 into 1 plus mu. Mu is equal to 0.3. Mu is equal to 0.3. And the answer is 76.96 megapascal. Sorry, gigapascal. 76.96 gigapascal. 76.96 gigapascal. That's the correct answer. The principal stresses at a point inside a solid's object are sigma 1 is given. Here sigma 1 is given 100 megapascal, and sigma 2 is equal to 100 megapascal, and sigma 3 is equal to 0 megapascal. 0 megapascal. The yield strength of the material is 200 gigapascal. The yield strength of material is 200 megapascal. Therefore, yield point stress is equal to 200 megapascal. 200 megapascal. The factor of safety calculated using Tresca's theory or maximum shear stress theory is mu 2, and the factor of safety calculated using von Mises maximum distortional energy theory is NV. Which of the following relationship is true? So we need to compare the factor of safety calculated using Tresca's theory and factor of safety calculated using von Mises theory. So first I am considering Tresca's theory. According to Tresca's theory, yield point stress by factor of safety, here factor of safety is NT, yield point stress by NT is equal to, in Tresca's theory the equation is sigma 1 minus sigma 2. Here we cannot use sigma 1 and sigma 1 minus sigma 2 because sigma 1 and sigma 2 are same magnitude. So shear stress is equal to 0 and this theory cannot be used. Therefore we need to use sigma 1 and sigma 3. Sigma 1 minus sigma 3. And yield point strength is 200 megapascal. 200 by factor of safety is equal to sigma 1. Sigma 1 is equal to 100 minus sigma 3. Sigma 3 is equal to 0. From this, factor of safety n is equal to 200 by 100 is equal to 2. Factor of safety calculated using Tresca's theory is equal to 2. Now we need to find out the factor of safety using von Mises theory. According to von Mises theory, According to von Mises theory, yield point strength by factor of safety NV the whole square is equal to 1 by 2 into sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square. Here sigma 1 is known, sigma 1 is equal to 100 megapascal. Sigma 2 is also given, sigma 2 is also 100 megapascal, and sigma 3 is equal to 0. By using these three values, and yield point stress is also given, yield point stress is 200 megapascal, and we can find out NV. We get NV is equal to 2. Here we can see that the factor of safety calculated using Tresca's theory and the factor of safety calculated using von Mises theory are same. So NV is equal to NT. Factor of safety is same. So option C is the correct. NT is equal to NV. Then 2.19, a shaft with a circular cross section is subjected to a pure twisting moment. We have a shaft and I am applying pure twisting moment. The ratio of maximum shear stress to largest principal stress. You need to find out maximum shear stress by largest principal stress, sigma 1. I am considering a shaft and applying with a twisting moment T, and I am considering an element on the surface of the shaft, and it will experience shear stress in all directions as shown in this figure. So this is the element on the surface of shaft, and this is the stresses acting. Here sigma x is equal to 0, sigma y is equal to 0, and tau xy is equal to shear stress tau. Then in this figure we need to find out maximum shear stress. The maximum shear stress is equal to square root of sigma x minus sigma y by 2 the whole square plus tau xy square. Sigma x is equal to 0 and sigma y is equal to 0 and sigma tau xy is equal to tau. So we get maximum shear stress is equal to tau. Maximum shear stress is equal to tau. Similarly, we need to find out maximum normal stress. The equation to find out maximum normal stress is equal to sigma 1 sigma 2 is equal to sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 the whole square plus tau xy square. In this case also sigma x is equal to 0, sigma y is 0, sigma y is equal to 0, and only sigma tau xy is present. In this case also maximum principal stress sigma 1 is equal to tau. Therefore maximum principal stress and maximum shear stress are same. Therefore the ratio is equal to 1. The ratio is equal to 1. 1 is the correct answer. Option B. Option B is the correct answer. And 2.20, the state of stress at a point on an element is shown in figure A. The same state of stress is shown in another coordinate system in figure B. We need to find out component tau xx. We need to find out tau xx. This is a normal stress. Then tau yy. This is also a normal stress, sigma y, and tau xy. We need to find out these three values, normal stress and shear stress. Here it is written that these are stresses of same point in different coordinates. I'm writing this is plane AB, this is plane AB, and we can mark this plane AB in this figure. This is plane AB. In this figure, this is the plane AB. Actually, the plane AB of second figure is actually a 45-degree plane. It's a 45-degree plane in the first figure. So the stresses acting at AB of second figure is actually equal to the normal and shear stress acting on a plane at an angle 45 degree in first figure. So we just need to find out the normal stress and shear stress acting on a plane at an angle 45 degree of figure 1, because this is the stresses of same point on different coordinates. Here I am assuming this is x coordinate this is x coordinate and this is y coordinate. Here we can see that at this plane the shear stress is 0, so this is a principal plane, and in this plane also the shear stress is equal to 0, that also a principal plane. So we can write maximum principal stress in first figure sigma 1 is equal to P and the minimum principal stress sigma 2 is equal to minus P. And we need to find out normal and shear stress acting on a plane at an angle 45 degree. Since it is a maximum principal stress plane and the angle between maximum principal stress plane and the maximum shear stress plane is 45 degree. So this 45 degree plane is the maximum shear stress plane, or you can use directly, we can use equation to find out normal and shear stress acting on a plane at an angle theta. We have the equation normal stress acting on a plane at an angle theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. By using this equation, we can find out the normal stress acting on a plane at an angle theta. Here, we need to find out normal stress acting on a plane at an angle 45 degree. Here, theta is equal to 45 degree. Sigma x is equal to P and sigma y is equal to minus P, and tau xy is equal to 0 and theta is equal to 45 degree. We can use the equation or we can use concept also. In this case, substituting this value, we get normal stress acting on a plane at an angle 45 is equal to 0. Or by using concept, we can see that this plane, this 45 degree plane is a maximum shear stress plane. The normal stress acting on maximum shear stress plane is sigma 1 minus sigma 2 by 2. Maximum shear stress acting on a plane at an angle 45 degree, or the maximum shear stress of this figure is sigma 1 minus sigma 2 by 2. This is the maximum shear stress, which is equal to sigma 1 P minus P by 2, which is equal to P plus P 2P by 2 is equal to P. The maximum shear stress acting is P. Or we can directly use the equation. We have the equation to find out maximum shear stress or shear stress on a plane at an angle theta. By using equation, we can find out the shear stress acting on a plane at this acting on this plane, that is shear stress acting on a plane at an angle theta is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. Here theta is equal to 45 degree and sigma x is equal to P and sigma y is equal to minus P and tau xy is equal to 0. By using equation theta is equal to 45 degree, we get shear stress acting on a plane at an angle 45 degree is equal to P. We can use the concept or we can use the equation to solve this problem. Actually, this is the same state of stress, and this plane AB of figure 2 is a plane at an angle 45 degree of figure A. And the answer is normal stress is 0 and shear stress is P. Normal stress is 0 and shear stress is P. Option B is the correct answer.